children, today we will be doing with one of the very important topic of wave theory, that is diffraction of light. So today's topic is diffraction of light. Now we have already done with interference, we did with the follow-up Young's double slit experiment. So what exactly is the topic diffraction all about? Now diffraction means, suppose if you have got a wavefront, okay, and the bending of light, suppose if you keep an obstacle, you are keeping some obstacle on the path of rays, so at the corners of the obstacle there is a bending of light. So this bend, the phenomena of bending of light around the corners of an obstacle or aperture is mainly called diffraction. So it is just a phenomena of bending of light around the corners of an obstacle or aperture. So this is what. Now it is mainly of two types. We have got Fraunhofer and we have got Phrenol. Now the basic difference between the two is that in one case, when you take with a Fraunhofer, then what exactly you will get that the distance between the source and the screen is infinite, but in the other case it is finite. Okay, and in one we take the help of the lens, the other one we are not taking it up. So we are here to do with the Phrenol. We will just do with the Phrenol diffraction pattern. So this is the diffraction pattern due to a single slit also. You don't have to do many things, but you have to do with the diffraction pattern of a single slit. And in order to do it, we'll take an arrangement. Now let's see what is an arrangement about. This is the slit we have considered, and this is your screen. Okay, so here we have got the ray of light coming from here, and we have kept a lens here. Okay, this is one of the lens, and we have got, this is, let us assume this part is A, this part is B. Okay, and from here it is getting refracted, and it has been, this is point B, this is one, and from here it is just moving to this part. Okay, this is another one. This is the center part, what is O. So this is what we have got for O, and this is, if you get to see the path difference, this is point K. So we have taken this as equals to theta, and this distance we have taken as small d. Okay, so this is the source. Now what exactly is the arrangement? Let me explain. This is the first lens. What is the work of this first wave lens? It will produce a plane wavefront. You can see that it is being produced because when it is being kept, the source is being kept at the focus. So when it is being kept at the focus, you get a parallel wavefront. And then the lens second is there to converge the rays. Now here you will find that O is always the place of central maxima, or what we call central maxima, because the path difference here is 0. The distance from A to B and B to A is 0. So it is always the place of central maxima that you will get to white. You will get this as white, completely white. P can be any point. It can be a minima or it can be a maxima. So what exactly we will just, according to the Huygens theory, if we go, then the slit AB is made up of large number of parts, and according to Huygens, each part of is a source of secondary wavelets, and all wavelets originating from the same part are in the same phase, and this is the reason this becomes the place for central maxima, brightness. Okay, now we need to find out this path difference BK. BK is a path difference. Now if you get to say, if it is theta, this is perpendicular and this is hypotenuse. So sin theta is perpendicular by hypotenuse, or BK is equals to d sin theta. We are getting BK as equals to d sin theta. Now when we get to see, we all know that the center is the bright. So the next dark will be the condition for the additional minima. is d sin theta is equals to plus minus m lambda. M can be 1, 2, 3. It cannot be 0 because it is 0, then it is the mean the position O we are referring with. Okay. Now the general condition for the subsidiary maximum, that is for the general condition for subsidiary maximum, is d sin theta is equals to 2m plus 1 lambda by 2. So we are getting this. Lambda is the wavelength. Okay. Now when we talk about, so what pattern we are getting, suppose if this is the middle one, if we see the pattern, then the central is always the maxima, then slowly and slowly and slowly you will find that this is decreasing. The intensity is not same, but it is decreasing. Okay. So here from here, this is the first maxima, this is the second, and here we have got the minima. This is the case for the minima. Okay, so minima, it is lambda by d, and this is also lambda by d, this is also lambda by d, and the angular spread is this reason, and the angular spread is this reason, and the width of the angular spread, that the angular width of central maximum is sin theta equals to lambda by d, and we get 2 sin theta or 2 theta is equals to sin inverse. This is twice because we are multiplying, theta is sin inverse, so it is 2 theta, so it is 2 sin inverse lambda by d. So this is the condition we have got for the angular width. Okay, so there are some questions. If we use white light, what will happen? If we use if the slit is illuminated by white light, then the diffraction pattern consists of central white with few colored all over. Okay, what will happen if the slit is made narrower? If this is the slit, if you make it narrow, what will happen? So in this case, we have seen that the first minimum is given by the formula d sin theta is equals to m lambda, right? So in this case, the first minimum on either side of the central maxima occurs according to this relation. If the slit is narrowed, that slit is reduced, the angle theta will increase, and the angular spread, that is for the central maxima, will be more. Okay, thank you for watching.